So if there are any questions about last time, please ask now. And after that, I'll briefly review what I did last time and then start on today's lecture. Are there any specific questions? Okay, so we did two things last time. One is we convinced ourselves that combining with some guesswork, Newtonian gravity plus special relativity and doing some manipulations which I described in detail, we were led to the equation box of h mu nu plus a whole bunch of terms which I am not going to write down again. Is equal to some constant times the stress energy tensor T mu. So this, according to our analysis, this should be the dynamical variable for gravity, rather than just the scalar function phi, which was the Newtonian potential. So we have many more dynamical variables in gravity than just the Newtonian scalar potential, as a consequence of trying to combine gravity, Newtonian gravity, with special relativity. This situation is familiar from electrodynamics, where if we just had electrostatics equations and then try to combine those with special relativity, we would be led to equations involving the magnetic field, which are not part of the electrostatic equations. Okay? So those
each bar. Here, equation, each bar.
No, this is h. Because I may have written, well, since I haven't told you what the dot is, I wrote you some equation which involved h bar and then some dot, right? But how does h bar and how are h bar and h related? They are the same, except that we subtract half eta mu nu times the trace, so that all goes into this. So here h or h bar doesn't matter. If we want to know exactly what are these things, then we have to decide whether it's h or h. Okay? Anyway, so just as magnetism is an inevitable consequence of relativity given electrostatics, so also all these extra components are a consequence of special relativity given Newtonian gravity. And on this side, instead of matter density, we have something called the stress energy tensor, and we'll be studying this in more detail as we go along. So this was one fact that we derived last time, and the second fact was that this equation has a kind of local symmetry or invariance under variation of h mu nu is being given like this for any arbitrary space-time dependent vector psi mu. Actually, this was not quite the equation. This was the equation around flat space for small h. If h is large, then you have to correct this ordinary derivative by something a little bit more complicated. Actually, if you, I guess I wrote that last time, didn't I? Did I? I mean, both equations are completely derivable. So maybe I should write the full equation. Then I'll lift this restriction. There is no restriction. This is true. And with d mu sin mu equals the ordinary derivative minus something involving the Christoffel symbol. Now, as we go along, you will see more and more occurrences of this covariant derivative and this Christoffel symbol, and sometimes you might feel that you're sort of lost. Whenever you feel lost, just remember to go back to the equation of a free non-relativistic particle moving on the surface of some space with a metric, which was, if you remember, Gij x dot I x dot j. The equations of motion of that will define for you what this Christoffel symbol is, and many of the properties that we want to know about curvature and about metrics, almost all can be derived from that. So if you ever feel lost, please go back to the very first lecture and revise your understanding of this symbol. Today we will derive some more properties of it. Okay, so this is what we did last time. Now what are we going to do with these insights? Well, the first insight I've already said is that gravity involves something called h mu, which has many components, but this particular transformation law, being a symmetry of the theory, tells us that, okay, so this is the transformation of a metric under infinitesimal coordinate transformations. And the coordinate transformation is therefore that x mu is replaced by x mu plus some vector psi mu of x, which is taken to be small. This is an infinitesimal coordinate transformation. So it says if I have some space-time coordinate describing a particular point, then this new function, which is this plus this, is another coordinate describing the same point. It's just a change of coordinates. And again, if you ever feel lost with changes of coordinates, think about the two different coordinate systems we introduced last time to describe a two-dimensional sphere, and you'll be convinced that changing coordinates is a very reasonable thing. Indeed, the whole point of geometry is to understand in terms of coordinates the things which don't actually depend on coordinates. Okay? Coordinates are like a crutch which we have to use to understand things, but geometry itself doesn't depend on coordinates. Therefore, by understanding it in many different coordinate systems, we actually understand it better. Okay. Now from here, we abstract the physical principle from these results. And the principle is the metric of space-time is a dynamical quantity and it encodes the force of gravity. Okay, so this is very crucial, worth underlining and worth thinking about a few times. Okay, it's actually a change of point of view, because in special relativity the metric of space-time is eta mu nu and it doesn't encode any force. Okay, but that's perfectly reasonable because special relativity is a theory which is correct in the absence of gravitation. When there's gravitation, special relativity is no longer correct. The reason why we study special relativity without worrying about gravitation is that it applies to all sorts of other systems like electrodynamics and so on. It applies to particle physics experiments, it applies to things which we can see at the Large Hadron Collider which is going to start up soon, because in all such situations gravity is of absolutely no consequence. Okay? But when gravity is of consequence, as in this course, we cannot consider the metric of space-time to be eta mu nu. We must consider it to be a dynamical quantity, and the amount, the variation, the function that determines this metric is in fact the gravitational potential in its most general form. And in particular, some component of the metric, going back to this equation, some component of the metric in some limit will behave like the Newtonian potential. We also last time did a calculation saying let's assume a particular kind of metric for space-time, and we derived from that that the geodesic equation in that metric is nothing but Newton's equation. So the whole picture is very consistent. Okay, so what do we want to do next? I'd like to first of all tie this up with the way Einstein chose to describe his ideas about general relativity. He didn't actually, I think, present it in this way, that if we combine Newtonian gravity with special relativity, we inevitably end up with general relativity. But he instead thought very deeply about a principle called the principle of equivalence, which leads to the same conclusion. But in a slightly different way. Now, what is the key idea in this principle of equivalence? So this is the kind of subject where Einstein introduced a lot of thought experiments, which is a very nice way to do experiments. You don't actually have to build anything. You just imagine things and try to see from consistency what kind of physical principles you can derive. And the most famous experiment that he designed in this context was that of a freely falling lift. Okay? So let's think about it and see what principle it leads us to in the context of gravity. So the idea of a freely falling lift is that there's something which is a closed enclosure, very comfortable inside. There's a person inside, but that person cannot see out, and that person just has to judge what is going on, what physical laws apply, by doing some experiments inside this box. The box, in the meanwhile, can be at rest with respect to something, or it can be moving, it can be in a gravitational field, or it can be not in a gravitational field. So the first thing we notice is that if we are inside this box and it's in outer space far from any source of gravitation, okay, then we'll be weightless and we'll be free to float around inside this box, and we'll say we are weightless, how nice. Okay, so that's just a fact. The second thing we notice is that, well, now supposing I bring this whole apparatus close to a very powerful source of gravity such as the Earth and let it fall. Okay. Now there are two things I can do if I bring it near the Earth. One is to hold it at rest. For example, I build a huge pillar 30 miles high and I put this box on top of it and it's at rest there. Okay. In that case, obviously, I feel some downward pull and I could say that the Earth is here. Well, I can't see where I am, but possibly we are somewhere above the Earth. From my measurements of the force that I am experiencing, I calculate that we are 30 miles above the surface of the Earth. That's what I am feeling is the force of gravity that the Earth exerts at that height. Okay. Now, imagine this pillar is removed and this thing starts falling. Okay. And it's freely falling towards the Earth. Now, the interesting thing is that I'm moving under the influence of the Earth's potential. The lift is also moving under the influence of the Earth's gravitational potential. Okay? And my mass and the Earth's mass are of no consequence because, as you saw in Newton's laws, the mass cancels out on both sides. That's why we say that the Earth gives us an acceleration due to gravity of 9.8 meters per second. And we don't say, well, it's different for each person. The force is different for each person, but the acceleration is exactly the same. Okay, that's another principle of equivalence preceding this, which is the statement that inertial mass and gravitational mass are the same. But because of that principle, it seems that I can't possibly say what's happening when this thing is falling to Earth. I can't possibly say that I'm in a gravitational field because again I'm weightless. Okay, I'm in this box. The box is freely falling in a gravitational field. I'm freely falling in the same gravitational field. As far as me and the inside walls of this box, I'm simply weightless, as much as I would be if I was in outer space far from any gravitating body. Okay? What's the conclusion from this? That in a freely falling object in a gravitational field, the gravitational field is somehow cancelled. Okay, the effect of the field is somehow cancelled as soon as I change my frame of reference to be with respect to the box. Of course, if the box developed a window and I looked outside, I could see that I am moving relative to other things. I might pass other objects and I could say that I am moving. But as long as the box is sealed, purpose of sealing it is to say that my only frame of reference, the only thing with respect to which I can take measurements. Yes, sir. Take. What do you want to take? Okay. So, if this is the only frame of reference or the only thing with respect to which I can take measurements, then I'll never possibly know that I'm in a gravitational field. I'll simply say that I'm weightless and therefore I'm experiencing no field at all.
So is this only valid if the gravitational field is a constant one?
Yeah, let me give my lecture. At the end you can ask the question. Okay? I don't mean at the end, but please wait until I finish what I'm doing, because I'm going to address all these issues. Okay. Now, this principle has the following interpretation if I think in terms of geodesics. If you remember last time, we thought of motion in a gravitational field in two ways. One was that it's a Newtonian potential, so the equation is x dot is minus grad of phi. Okay, that's the force I feel, that's also the force the lift feels. The mass cancels out and we have some principle of equivalence. But another way of thinking about it is that both are moving in a geodesic in the curved space-time given by some metric. So we just wrote, and I just rubbed it out, that gravitation is nothing but curvature of space-time, or it's nothing but a metric of space-time. So the lift is falling as per a geodesic of that metric. I am also falling as per a geodesic of that metric. Result is basically the same. Now let's think about this geodesic a little more carefully by drawing the Earth. And you see that now my lift is disproportionately large compared to any imaginable lift. But that's the nice thing about these experiments, that we don't have to worry about realistic details. It has to be in principle meaningful, not practically possible. Okay. But now I notice that actually the principle of equivalence isn't quite true for a reason which this diagram makes immediately obvious. Namely, I'm inside and I'm assuming I have all the experimental equipment I need available to me. So on a table, which is a few thousand kilometers across, I place two objects, and it's a frictionless table. And I wait for some time in this lift, and I notice that these two objects have started moving towards each other. Okay, why is that? In a Newtonian picture, because it's attracted, this one is attracted to the center of the Earth along this line, and this one is attracted to the center of the Earth along this line. In the geodesic language, it's the same thing. This is the geodesic of the Earth's gravitational field. Okay, it's the path along which you will travel in a gravitational field is a geodesic. Okay, because you travel to extremize your distance. And this is another geodesic. And you see that these two geodesics are converging. Okay, if they are converging, then it means that although the normal component, if I fix some reference thing, I may find that this is approximately weightless inside this lift, but if I wait long enough, I will find that these two things are starting to move towards each other, and I say, well, that's a strange kind of gravitational force, but it's a gravitational force because I'm using objects which have no other charges or anything, and yet something is influencing their motion. Okay, that tells me that in a large enough lift, particularly large enough to sense the inhomogeneity, so this gravitational field is not all four lines of force strictly parallel, there's a focusing effect because the center of the Earth is there. As long as I'm big enough to detect that, then I can actually distinguish between being in a lift in outer space and being in a freely falling lift. Okay? So, let's extract two principles from this. One, over a very small distance scale, geodesic motion in a gravitational field is undetectable. So this is the principle of equivalence. It says if the lift was a point-like lift and it was falling freely, not only necessarily towards the center of the earth, but actually in any complicated gravitational field you like. The important thing is that the whole lift be very small and it be allowed to fall freely. That gravitational field might be due to 200 planets and it might be very strangely curving and all that. That doesn't matter. The important thing is I inside the lift and the lift both have to be small and both have to travel freely. Then I'll never know that I'm traveling. I'll be always weightless and free of gravitational force. So that is this. But the second statement is once size effects or inhomogeneities or variations in the gravitational field, whatever you want to call it, are included, then the gravitational field is detectable. This suggests, and I'm going to make it more precise, that there is some concept as per which in a local region my freely falling lift, which is nothing but a change of coordinates, can take away the effect of curvature, can take away the effect of a metric, but that can't be done in a region that's sufficiently finite. It can be done in a region that's infinitesimal. Okay? That point clear, sort of conceptually. Now we'll write some equations based on it. Now you see, these two statements are about gravitational field, and here I want to list for you sort of my approach to mathematics of this problem, that there are really three kinds of mathematical systems which we will study in order of complexity. So here is Euclidean 3 space, or Euclidean 3 space. Okay. Here is curve 3 space with a metric, and here is curved space-time. So 4 space-time, 4-dimensional space-time with a metric. So obviously all our interest is concentrated in this box. This is what this course is about. But having come to some conclusions, I want to test them or to explain them or to develop them more by going back to this place, because this is a much more familiar place to be. This is really a radical theory that's very hard to grasp because it involves space-time. You cannot talk about time and space as distinct in curved space-time. But in curved space, you can certainly think of time as distinct. You can imagine geometry. 3-dimensional geometry is actually not so easy to imagine, but you can do 2-dimensional as an example, and so on. So now, and many times in the course, whenever I am faced with some issue which requires me to understand geometry better, I'll go back to conventional geometry. I may also rely on Euclidean geometry, which is even simpler. Okay, I don't know where in these boxes to put Minkowskian force space. That actually sort of is like a bridge between here and here. Maybe it should be put in the middle. If you think about it, these are the two things we combine to get to general relativity. Okay? So I'm going to use that, and for the rest of this lecture, I'm going to forget about gravity and try to understand what these two kinds of statements might correspond to in ordinary curved space. Okay? And the curved space, whenever you feel lost about curved space, imagine the surface of a sphere. But also imagine more general spaces which are not so incredibly symmetric. That the sphere is extremely symmetric. All possible rotations you can perform about the origin, leave it invariant. Imagine that you take a sphere and you sort of punch it here and there so that it develops some kind of bumps, a wobbly kind of thing. That's quite a general curved space to be thinking about. So we'll think about that. So in ordinary space, when I say ordinary, I mean in the sense of space rather than space-time. Is there a concept similar to principle of equivalence? Now clearly, there can't be literally such a concept because this principle has to do with freely falling objects in space-time in a gravitational field. I want to forget about space-time and forget about gravitational field. I want to ask, does a curved space have a property that there is some frame of reference, which means a choice of coordinates, so that at a particular point, I don't know about its curvature? Okay, so let me state the question more precisely. Does a curved space with metric G, I, J of X have the property that at some point or points or regions, we'll find out, the metric can be made to look trivial by a choice of coordinates. What's a trivial metric? Delta ij would be a trivial metric. Yeah? Just one identity in a space. That's what would cause us to say, well, essentially there's no metric. It's just a familiar Euclidean space. Euclidean space has the metric delta ij. So the question would be then, can we, in other words, look for some new coordinates x prime I as functions of x such that g prime ij at x prime equals delta ij at some particular point, regardless of the original metric. This is very important. When I say regardless of g, I mean the following. Whatever metric I give you, gij of x, given that metric, I can find some new coordinates such that the new metric in the new coordinates is delta ij at a particular point. Is that possible? And the answer I claim is yes, and we'll be demonstrating. Okay? Now here there's a little bit of notation I want to introduce because this issue is always confusing. Let P be a point of the space. This notation P is an abstract notation denoting a particular point. The reason it's needed is that point will have coordinates, some value in the x system and some other value of coordinates in the x prime system. Okay? If I want people to only remember the fact that this is the same point whether I'm in the x system or the x prime system, I'll just label it P. Then I can say Gij as a function of P and G prime ij also as a function of P. What I'll understand is that this has to be evaluated on the coordinates of P in the x system, and this has to be evaluated on the coordinates of that point in some x prime system. Okay, there's an example. The north pole of the earth is a place. There could be people there, or this room is a place. Okay, so this room roughly is a point P on earth. Okay, is the same point whether I use latitude and longitude to label it, or I use some other coordinate system developed by some other civilization to label it. Still the same room. Okay, so the room is P. Okay, the value of P may be x1, x2, x3 equals so many, so much and so much, or it might be y1, y2, y3 equals some other numbers. That's not important. It's the same point. So please try to keep that in mind, because I always get people always get confused about what this means. Okay. So now the question is, for a fixed P, try to make G prime ij of P equal to delta. So I like to say it in this way, then I don't have to worry what I write as the argument. Okay. Good. Okay. So here's a very simple way to show that this can be done. Okay. How does G transform under x going to a new coordinate system x prime I of x? We get a new metric G prime ij at any point x prime to be equal to these factors. This is the rule of how the metric changes under a change of coordinates. Okay. Now let me specialize this equation to be evaluated at a particular point P. So this is evaluated at that point P. This is evaluated at the same point P, and these two things are also evaluated at the same point P. Okay. Now let me use the notation that M L J is nothing but dxl by dx prime j at the point P. Okay, this factor. So with this notation, I can write that G prime as a matrix is M transpose G M. Is that okay? Just using matrix notation. If this is true, then G prime ij should be M transpose ik gk l m l j. You can put in matrix indices for matrix multiplication. People are looking stunned. You have seen matrix multiplication before. Okay. Is it difficult to decipher that from this? M is coming last. M L j is dxl dx prime j. That's this factor. I'll just write it here. This one is contracted with k with this, but k is its first index, I is the second index. But if I write a transpose, then the first and second index get interchanged. So that's the equation. Okay. Now G is real and symmetric as a matrix, so it can be diagonalized. By some orthogonal M. Okay, so I've got it to be diagonal. That's not yet what I wanted. I wanted it to be delta ij. I've only got it to be diagonal, so it has some diagonal entries. So what's the next step? Scale. Very good. So it's that simple. Next, scale the coordinates. You see, sometimes just words are more useful than equations. We are doing it in two steps, but of course, if I do one change of coordinates to make it diagonal and another one to make to rescale, the whole thing together is some change of coordinates. Okay, I'm doing it in successive steps. But at the end, I've got G prime in these new final coordinates to be delta ij, so I've proved that it can be done. Okay? So now we come to a very important question. I can do this at a point. Can I do this in the same coordinate system? Can I make this happen over a whole finite region? And turns out the answer is no, I cannot. That is, given a metric, I can't make a coordinate transformation which returns for me a new metric which is delta ij over any finite region. If you think of Taylor's theorem, which tells you how to expand a function, you know that knowing a function at a point is very little information. Okay? Knowing it over a region, small but finite region, you know actually all the Taylor coefficient, the expansion coefficients in its Taylor expansion, right? So you need to have infinite amount of data to know the function in a region. Okay. So out of that infinite amount of data, we have only fixed one. Yes.
Sir, but for different regions, you can find different ends which can again transform it to delta.
No. Think of my statement. My statement was, can I find an M such that, first of all, M is only the change of coordinates at a point P, at a particular point. Okay. So don't use M anymore. Think of the change of coordinates over a whole region. Okay. Now over that whole region, the question is, can I make the whatever, however small you like, however small, of size epsilon, but finite, not zero, not 1 point. Okay? It should be a region. If you understand the difference between a point and a region, that's a point. Okay? And that's a region. Over a whole region, can I make the metric delta ij by a change of coordinates? Answer is no. I'll prove it to you. Okay?
No, my question was, you take some other points at P prime.
Yes.
And you evaluate some other M prime.
Sure.
Then that M prime can transform it to the Gij dash.
Yes.
Evaluated at P prime.
Yes, will be delta ij at P prime, and now it won't be delta ij at the original P anymore.
Yeah.
So of course, since I haven't specified what is P, this is arbitrary, but fixed. So what you are saying is just change, can I change P? Can I put P somewhere else? Yes, I can.
Yeah.
I can certainly choose any P I like. So this is the content of it, that I can make it delta ij at any point, but not at more than 1 point simultaneously. And forget more than, most importantly, I can't make it delta ij over a region. Okay. If I could, I would have to fix not only the metric to be delta ij, but also its first derivative, second derivative, third derivative, fourth derivative, so on up to infinity, all to be 0. And that's what I can't do. Okay, is that point sort of clear? Very important. Are you seeing some connection between this discussion and that discussion up there? Okay, these are the kind of things which later we'll begin to understand. What are the finite size effects or inhomogeneities which enable us to detect the gravitational field? Okay, so I'm building up to that. So this is one result. Now let me give you the second result. After making Gij at P, I've dropped the prime because now I assume it's done and I'm no longer putting a prime on that coordinate system. So Gij at P is delta ij. I can also make the first derivatives Gij, comma k at P, which means d by dxa of Gij evaluated at P equal to 0. All first derivatives in the sense I, j and k run over all possible values. We usually have in mind 3, but it could be 2 or it could be anything. It doesn't really, the number of dimensions of our space makes no difference to these things. So this is a new statement. Okay? Of course, preserving. I make this transformation, but of course I preserve that Gij P is delta ij. So I do this and this. There will be no fun if after doing this I make a coordinate transformation which enables this result but it undoes that result. There's no point in that. Both I can do simultaneously. Okay? So we have to prove that now. So there are many ways to prove it. One is a counting argument, but I find the nicest way, I got it actually out of Landau and Lipschitz's book, and I'll do that. And then, so I'll start again here, and I'll just show you the proof, and then we'll do some counting. So, statement is, we can make Gij at P equals 0 and, delta ij and Gij k P equals 0 by a choice of coordinates. For the proof, let's assume I've done the first thing because I've just shown you that it's possible. Okay? And after we do it, let's also shift the coordinates just by a translation so that this point P is the origin of those coordinates. You can easily do it without that shift, but it's convenient to shift. So assume Gij P equals 0 in the xi coordinates where P is xi equals 0. So we need to prove the second thing. Okay. So what I'm going to do is to first of all recall, and this will be quite illuminating. Let me recall for you this symbol which keeps cropping up. I hope by now everybody has tried to derive the geodesic equation in which this symbol appears, and if people need help we can talk about various ways of remembering it. You see that this is one of the few things that even at my age I can remember how the indices are placed. That's because it has this nice property, one index is up, so that has to be raised by some inverse metric. That leaves three indices L, J and K. So there are three corresponding terms. The ones where L is an index of G are symmetrized in J and K because after all on this side this thing is symmetric. Finally I subtract G with J and K, comma L. So it's quite easy to remember once you get used to it. And Landau and Lipschitz use this nice notation that this is also called gamma IL, GIL, gamma LJK. Gamma with all the indices lower. Okay? This defines this gamma. And if I want to define it, if I want to invert this relation, I just contract with G on the left side and I'll get the right side. So we are recalling this because it depends on first derivatives of the metric. Okay? And what we'll show is that there's a coordinate system in which this can be made 0. And then we'll show that if this is 0 in all components, then each of these terms is 0. That's the second step. Okay? But first let's show that there's a coordinate system in which this is 0. So, very easy. Let x prime I be just a shift from the original xi by the amount gamma ijk at 0 xj x. Because remember, I'm trying to do all this at the point 0. It's the point P which is now equal to 0 in the x coordinates. Yes.
We choose the point P to make Gij 0, is it?
Yes. Gij not 0 but delta ij.
Delta
Gij has been made to delta ij. Yes. I assume it because I've already proved it at the bottom of the board.
No, but you assume it to be delta ij, not 0.
Ah, 0, 0. Just a typo. Sorry. Somebody should have. Thank you. Yeah. Gij of course cannot be 0. That's a very singular point of the metric, and that's one of the weird things about reality, that normally when you have fields like electromagnetic field, then the absence of field means 0. Here actually the field is not Gij but Hij in some sense. Hij is the deviation of Gij from delta Ij. So H is 0, G is delta Ij. Okay, so I make this coordinate transformation, excuse me, with the minus sign. Now the first thing to check is that this preserves the condition Gij equals delta Ij at 0, does it? Can you see by inspection that after I make this coordinate transformation, Gij is still delta Ij at the point 0? First of all, when x is 0, what is the value of x prime?
0.
Also 0. But secondly, if I look at the derivative of x prime with respect to x, this is delta Ij, but the second term, because it's quadratic, okay, at the point 0, it doesn't contribute. Okay, so at the point 0, the transformation from G to G prime is just delta Ij. So if G was like that, it remains like that. Is that clear? Okay. Now, what is gamma prime IJK? How does gamma transform when we transform coordinate systems? How would we find out the answer to this? It's all on the board, right?
We know the transformation.
We know the transformation of G, we plug it in here. Okay. However, there is a derivative acting on G. That derivative will differentiate not only G, but also the factors, the Jacobian factors del x by del x prime, which come in front of it. So we can get a bunch of terms. So as usual in this subject, you can get slightly complicated formulae. But at this level, they are all extremely simple to derive. And even if you forget where everything came from, you can go back to first principles, which I emphasize should be thought of as that particle moving in a curved space, that Lagrangian. Everything will come from there. Okay. So it's an exercise. This I'll probably put in, I'll be giving out some homework set soon. So the exercise is the following. So let's try to write down things properly. This has two terms on the right side, one which involves gamma and another which turns out doesn't involve gamma at all. It's an inhomogeneous term. So to figure out how to write it, let's put gamma lmn. There are going to be three Jacobians. I'm doing this slowly because it's convenient to do it. It's convenient not to try and memorize it or pull it out of a book, but just reconstruct it as you go along. So there are going to be three. Now, each of these has to have one of them x and the other x prime. How do I decide which is which? And also each of them has to have these three indices and these three indices. Okay. So, sorry?
No, one at the above will be x prime and two
Yes,
at lower.
yes, but I'm just telling you how I always remember it. Maybe you have a better way, then you can use that. Okay. So here I have to get rid of indices L, M and N. So L has to be here because L here being an upper index in the denominator, it actually is a lower index. Okay, so it can be contracted with that. And this has to be M and N. Okay. The next thing to remember is that if they are contracting with gamma, which is a function of x, then all these three must be x and not x prime. Therefore, the other three must be x prime. And finally, what indices must they have? This must have I to match with that, and these two must have j and k. So this gives you the proper placement of indices whenever you transform a tensor. I know people are used to it, but there are also people here who are not used to it. So I'm just spelling it out. This is one term, but it's not the whole story. There's one more term, and it comes from what I told you, that when we differentiate the transformation law between g and g prime, some terms come by differentiating the del x by del x prime factors themselves. So we get a new term, and this new term, it's not to get it wrong, is this factor is the same as here, and the other factor is del 2 x, right, del x prime j k and then these two terms. Okay, so this is a general rule. Everything is evaluated at whatever point. Now, for this general rule, in this general rule, I will plug in the coordinate transformation that I proposed, which is x prime is x plus some term in second order n. Okay, and then I evaluate this at the point x equals x prime equals 0. That's my point P. So at P, I'm using the above coordinate transformation. Gamma prime ijk at P, or I can as well call it 0, is all this stuff. Now all this stuff at the origin is just deltas. We've chosen our coordinate transformation that way. So it's gamma ijk at 0. The second term gets a contribution from, it doesn't get any contribution from here because the second derivative will kill this term. But the second derivative acts nicely on this term and it also tells me that I made a mistake. There should have been a half. So when I perform the second derivative on that term, okay, now you may object that I have got my primed and unprimed mixed up, but actually it doesn't matter too much, but I have actually got them mixed up. So perhaps what I should have done, okay, it doesn't matter much, but perhaps what I should have done was to define the change of coordinates by saying I think it's okay. So I'll call this plus. Okay. Now how do I evaluate this term? See, all these single derivatives evaluated at the point P are trivial because they are all identity. So whether it is x over x prime or x prime over x, they are all identity. This is the only interesting one. And this one is del 2x by del x prime j del x prime k. So for that I have to take this to the other side. Okay, so this, if I invert it as x in terms of x prime, I'll get this coefficient the same with a minus sign, and then there will be many more terms, but those more terms will all vanish at the origin. So this change of coordinates I can also invert to solve for x in terms of x prime, and it will be the same function with the minus sign. Okay, from that I'll find that this second term just gives me minus gamma ijk of 0, and I'm done. A lot of noise about nothing. I just showed you that I can make gamma ijk vanish by simple change of coordinates. Okay. Important thing being, whatever it was, I can just remove that much. Okay. And the lesson from this particular change of coordinates is that it is the second order term, the quadratic term, and is the only term that counts. If there were some cubic and higher order terms in that change of coordinates, they would not contribute to this process at all at the point 0. They would contribute at some other point, but not at the point 0. That's clear now? Okay, so this is a very visual and practical way of showing you that gamma can be made 0. Again, it's powerful because all components of gamma have been made 0. This is lots of components. How many values does I take? D values in D dimensions, and this takes D into D plus 1 by 2 values because it's symmetric in D coordinates. So that's a whole lot of values, and all of them simultaneously can be made 0 at the same time as all the components of the metric have been set to be the identity. Okay. Now you may wonder how long this is going to go on. What can I do about second derivatives of the metric? Can I also put those to 0 by a coordinate transformation? And if that were true, then, and if you could put all derivatives to 0 by a coordinate transformation, then you would have the result that the metric Gij is delta Ij in a finite region. How big that finite region is depends on radius of convergence of your Taylor expansion, but it would still be a strong statement, and in general that statement is not true. So I have to now convince you that I cannot make second derivatives 0 by a coordinate transformation in general. There could always be some metric in which I could make the second derivatives vanish by coordinate transformation, but that would have to be a very special metric. In general, cannot be done. That's the statement. So let's try to understand that. Oh, before that I should have actually completed something which I started doing here. I've only shown you that gamma can be made to vanish. I haven't shown you that all the derivatives of G can be made to vanish. Right? I should show you that all the derivatives of G can be made to vanish, but actually it's very simple, because let's look at gamma with all the indices lower. I defined it there. So gamma Ljk is equal to Glj half Gljk plus Gj minus Gjkl. To this, let me add gamma Jlk. I just commute the first two indices and add up the two. So I get okay. Now I add both sides of the equation. What's the right hand side? This cancels with this, and this cancels with this, and these two are equal. So the half goes. So now I am done, because I have shown you that I can make this 0. If I can make this 0, then with one index lower, it's also 0. All components of this are 0. This is also 0. I add them and I get this to be 0. So all components of first derivatives of G are all 0. So now we can focus on second derivatives. Okay, so let's redo what we did earlier, but in a little bit more abstract language, just trying to count components. So first, for Gij equals delta Ij, which we already convinced ourselves we can do, how many conditions did we need? We needed, so how many independent components of this were there? If you are in d dimensions, then d plus 1 by 2. Right? Conditions. And we have in achieving that, which aspect of the coordinate transformation do we need? We actually need only the linear term. Because remember, we needed to fix that matrix M. Okay? And that matrix just came from evaluating del x prime there by del x at 0. We didn't need any of these terms. Okay? Now, in general, del x prime by del x at a particular point are d times d or d squared equations. Okay? So we have d squared quantities available. We are free to choose all of these. Okay. So does this counting tell us that it's possible? We need to impose so many conditions and we have so many quantities at our disposal. Okay, it's basically the general matrix. If you make a linear transformation between x prime and x, that matrix has d squared entries, and the question is d squared greater than this? So of course it is. In fact, it's quite a lot greater, and in fact there's quite something left over. What is the thing that's left over? It also has a nice meaning. Okay, so we actually need only these. So d squared minus d plus 1 by 2 are still left over. And this number is d into d minus 1 by 2. What is d into d minus 1 by 2? Reminds you of anything? Yes. So what physical operation does it remind you of? Rotations. Okay. The point is that after we bring the metric into this form, the theory is still rotationally invariant. So rotation simply preserves this form. So this tells us that not only we can bring the metric into the form delta ij at a point, but we still have a whole bunch of coordinate transformations allowed after doing that, which don't spoil that form, and they are the rotations. So that rotations are always there. Good. Now let's go to the next step. So 2. For g, I, j, comma k equals 0, how many conditions do we want to, does this amount to? How many conditions are these? How many components does this equation have?
D square into d plus 1 by
Good, thank you. D squared into d plus 1 by 2. Conditions. And this time it needs to be, they need to be imposed by the second order change of coordinates. Del 2xi by del x j del x k. How many conditions are, how many quantities are these? No.
again this
Again this. So we see that making the first derivatives of g equal to 0 can be imposed by choosing a quadratic term as freely, choosing an arbitrary quadratic term in the change of coordinates and fixing it to be whatever will make this thing equal 0, exactly the same number of variables. This is what we already did. Okay, it's also the same number of components of gamma ijk. Okay, so now you can see where we want to go from here. Supposing somebody came along and said, let's make this equal to 0. How many conditions are these? So these are making second derivatives equal to 0. So this is d squared d plus 1 squared by 4. However, the coordinate transformations which will do this, if they are there, are three of them. Are third order, cubic coordinate transformations. So this is what I have to fix, and this number is d squared into d plus 1 d plus 2 upon 6, I believe. And now you see, let's evaluate this for d equals 3 just as a test. So I get 36 here, and here I get what? 30. Let's also do it for d equals 4. Come on, quick mental arithmetic exercise. First of all, check if I am right, I could be wrong. I think I'm right. What is it for 4? 100 up here.
170.
And below?
170.
25. So there are more of these than these. That's very bad news. That's opposite of what I was telling you. So I hope you're wrong.
80.
Yeah, that's it. Okay. So let's subtract these two. So we find that there are 6 second derivatives of the metric that are unfixed. 30 out of 36 second derivatives, 30 can be fixed by coordinate transformation without spoiling all that we've done before, but 6 remain unfixed. And out of 100 second derivatives in 4 dimensions, 80 can be fixed and 20 are left. Okay. And the purpose of this exercise will be made. Yes. Right. The purpose of this exercise will be revealed in due course, and this is really the key. So these are the number of components of the Riemann curvature tensor as we see in due course. And this quantity, along with its derivatives of course, will be the thing which we'll focus on to understand curvature in space-time. Okay? Because it is going to be defined in terms of second derivatives of the metric Gij.
Is this 6 parameters has anything to do with 6 parameters of Lorentz?
No. It has to do with 6 parameters of the Riemann curvature tensor in 3 dimensions. You can see what you can calculate this number. It's this minus this, whatever it is. It has a lot of factors in common. You can subtract them. Okay. Good. Okay, so that was a lot of simple manipulations with coordinates, and we concluded something hopefully useful, which is that physically in any system the value of a metric at a particular point is worthless. It's no information at all. And the value of the first derivative is equally worthless. That's also no information at all. It's only from the second derivative onwards that there's information. Until that time, it's all in your choice of coordinates. Okay? However, if I made the choice of coordinates which fix the metric and first derivative at one point, knowing the metric at another neighboring point is information. Okay? That is genuine information. So you see that this is in some sense should remind you of this fact that I drew earlier, that in the freely falling lift, 2 different objects fall in such a way that their geodesics approach each other. In fact, this leads us, or will lead us next time, to the concept of geodesic deviation, which I'll define and explain. So the idea here is that if I am one freely falling observer, then I never can tell the presence of a gravitational field. But if I have 2 freely falling observers near each other, any distance, however close, as long as they are not exactly on top of each other, then I can tell the existence of a gravitational field. And how will I tell? Because these 2 geodesics will start to converge or diverge. There will be an effect which has to do with the second derivative of the metric, okay, and then I'll be able to tell. Let's see this in yet another way. Single geodesic, the equation in space is just this. And we've just seen that at any particular point of space, I can cancel this term. That's just what we saw. Okay? Coordinate choice can cancel the second one. At any specific point. So what does the equation, geodesic equation, become at that point? This. Okay, it was always freely falling, whichever way you call it, it's freely falling. But this is even more than freely falling. This is that you don't even see the presence of curvature. You don't see the presence of the metric. It's the same statement as we just made, but made again. That in one geodesic you can always remove the second term. In two neighboring geodesics you can't. Okay, you could find a coordinate system which removes the second term from one of the geodesics at a point, but since the other geodesic is some finite distance away, you can't remove gamma from the other equation, and now there is a chance to measure that. So we've got some kind of picture. It's still going to build up more, and also we've been using the crutch of ordinary curved space and not yet curved space-time. But many of these results will be true also in curved space-time. For example, in curved space-time, we've already seen that the correct geodesic equation just has this indices mu lambda. It's the same equation. Okay. If you look at the procedures I just showed you for changing coordinates and removing, making the metric equal to delta ij, in space-time you can do the same thing but make the metric equal eta mu nu. Okay. Let me write those results here. Because if you saw, everything I did was really counting arguments. So it really doesn't depend on the signature of the metric, whether it's all space or space and time. So to summarize, and actually we've done very little in this lecture, but I think for me this is the core of what it means for space-time to be equivalent to geometry or to a metric. So I've spent a little extra time on it. So the summary is that in space-time, borrowing from all these things we did in space, one can choose a coordinate frame or a frame or a reference frame in which the mu, the metric of the whole space-time, at a space-time point P is eta mu. Okay. Since there is a signature minus plus plus plus, this is the best you can do. You can't make it delta mu, but you can make it eta mu, which is also physically sensible, because here we are saying that we can choose a coordinate frame which is accelerating along with the falling observer and cancels out the effect of gravity. So after that, the effect of special relativity should still be there, which is that space and time are still combined, but in a Minkowski space-time. And as before, g mu lambda at P can be made 0. And then, for example, the geodesic equation okay, first of all, so this is principle of equivalence. A sufficiently small, at any instant, a sufficiently small observer in a sufficiently small accelerator reference frame or sufficiently small falling lift can't tell the effects of gravity, because that person is working in a frame in which these things are done, and the person then says, okay, no gravity. Okay. The fact that when we make the lift a little bigger, we can start to see effects. I mean, actually, it's not just a little bigger, it's anything other than a point. Only an idealized point-like observer will see this. Anything bigger than a point, any finite separation between two objects in a gravitational field that's not homogeneous, we'll start to see the inhomogeneities, as I indicated in one of the thought experiments. And that will be the fact that this kind of derivative is significant. Okay, good. So next time I'll develop this theme a little more, talk about parallel transport, and what I'll try to do next time is to focus more on space-time rather than space alone, because space is kind of a crutch, it's a way to study geometry, but space-time is the place that we really want to be in. So from next time I'll talk about these equations in space-time context. And one of my colleagues, Nitin Nitsure, who's a mathematician, has volunteered to give you people a few lectures explaining what is a differentiable manifold, Riemannian manifold from a mathematical point of view. So in the spirit of this course, I think it will be nice to have a few lectures from him, and we'll arrange that. So I'll come to some place where I feel I've introduced some physical ideas, and then he'll give you these couple of lectures so that you will have your mathematical ideas clear, and you need not worry. He's one of the really very nice mathematicians who can talk language accessible to us. So we will come to that. Okay. Are there any questions? Yeah.
So, like, point that you were making about if you're in a small enough region, we wouldn't be able to say whether the ball will move towards each other or not. So, but our equations that we have developed so far, they offer no intrinsic length scale to which we can compare whether our distances are small or big. So, in what spirit are we saying that it is?
Yeah, I just told you in what spirit I'm saying it is, that the tiniest separation, even infinitesimal, will make it possible. That's correct what you said. So it's not like, so it depends on the resolution of my experiment, not on the gravitating system. In other words, this equation says that I can get rid of the effects of gravity by being in a freely falling lift only if that lift and I are strictly point-like. That's why at the beginning of the class I emphasized this fact that it's not even in a small disk-like region or a small open set in space-time or anything like that. Just at a point.
So if one designs a good enough experiment,
Yes,
it's always
absolutely. But on the other hand, this fact is still very non-trivial. Okay? And it's the reason why, in practice, if you were really in a freely falling lift and you didn't have a lot of experimental tools around, you really wouldn't be able to tell the difference between being in that. It's a physical statement. Even if it's very idealized and localized onto some point, it's a physically very meaningful and observable.
Is principle of equivalence just a statement that space-time is a matrix?
I suppose it could be. I mean, this is true in any metric space. It's true in a Riemannian manifold, and it's true in pseudo-Riemannian, which is with the signature. So the statement is anyway true. Nobody could argue with that. I think principle of equivalence says that. See, this is a very dry mathematical statement about a metric. Principle of equivalence says, first of all, space-time is given by a metric. That is, gravity is given by a metric, and secondly, therefore, I can't tell the presence of gravity if I'm in a frame in which the metric has this form. So it's both of these.
And because we started from the fact that g mu dx mu gives the space-time interval.
Yes.
Something like that can be defined. We took it a priori.
Yes, that's correct.
So if at the end if we did not have something
Yeah.
called principle of equivalence, then could we have justified that statement?
Yeah. I agree. I mean, so the question is, would it make any sense for space-time for gravity to be described by a metric and then not have the principle of equivalence? There's only a tiny sense, I think, in which it's possible. People talk of a weak principle of equivalence and strong principle of equivalence. Okay? So the strong one has to do with all other forces and interactions in nature. So somehow one could imagine, though it sounds very outlandish, that there's some other maybe electromagnetism in the presence of gravity behaves so weird that you can distinguish even at a point between a freely falling lift and an actual gravitation. That possibly makes sense. I certainly know people are still doing experiments to detect violations of that principle. But the principle of equivalence, as stated here, it's very hard to understand how it could be violated. Maybe what we should do is Google for violations of principle of equivalence and see what people are saying. It would be quite interesting. Yeah.
All the derivatives vanish.
Sorry?
That part. And you added
Yeah.
how much?
Yes. The first derivative, all components are.
You had said that from the previous statement we proved that the origin
Yeah.
gamma Lj 1k had vanished.
Yes.
So when you add this, what happens?
So this proves that individual components of the metric vanish. The gamma was the sum of three terms. So if gamma vanishes, you might say, well, it means that these three terms add up to 0. Doesn't mean each of the terms is 0. But by reorganizing the equation in this way, we see that each of the terms is 0.
Yes, sir. The eta mu is a Minkowski metric.
Yes.
So it is true when principle of equivalence is valid when the metric is the Minkowski metric.
No. It's not valid when the metric is a Minkowski metric. It's valid for all metrics. It's the statement that first of all, the statement that the effects of gravity are summarized by the metric. Therefore, non-trivial gravitational field will be equivalent to a non-trivial metric. Secondly, that there is always a coordinate frame in which that metric can be made trivial at a point. That's the statement. The metric is this at the point P. It's not this at the point P prime, even if P prime is a micron away from P. Yes.
Sir, here in a space station, we are not talking about space time.
Okay.
We are just want to know that whether a curved space with matrix Gij has a property at some point C, I can make it trivial. That can be done only with G minimum equals theta minimum.
If it's space, not space-time, then it's Gij equals delta I.
Gij equals to delta I.
Yes.
What to say about the sparse field?
That can be made zero also. I just showed that.
That can be made, but it doesn't. It is not required to support the statement that the space the space can be made trivial.
See, it's not trivial anyway. I think I won't use the word trivial. The whole point is the space can be as weird as I like, but I can still erect a system of coordinates such that the metric is identity at one point and the first derivative is zero. I don't have to erect those coordinates, so nothing is trivial.
What is the necessity of the first derivative to be zero?
What's the necessity of making the metric equal to identity? There's no necessity. I can work in coordinates so it's not identity. The fact that I can do it shows me that no information is contained in the value of the metric. I can make it identity, or I can make it 10 times identity, or I can make it any other matrix I feel like. Identity is like a reference. That's the simplest metric. You see, in this room, if I want to carry out a measurement, I might say this is the x-axis, this is the y-axis, okay, and they are of equal length, but I'm free to take my axis angles with respect to each other and define this unit, one unit this long and the other axis, one unit this short. I can do many things. Okay. The content of the statement is that there is no information contained in knowing the value of a metric or its first derivative in a given coordinate system at a particular point. Information starts being contained when we know the second derivative of the metric at a point, or when we know the metric in a region. Both contain information. It's merely at one point information is not contained in the metric, but only in it's only a question of coordinates. That's the thing. One shouldn't think that we are making the metric trivial. Actually, the metric is anything but trivial. Just imagine a round ball. Okay. First of all, the metric is the same everywhere, right? Because it's a round sphere. It's perfectly symmetric. Metric looks exactly the same everywhere. But I can still pick one point and make these two statements true at that point by choosing some coordinate system. Okay. So what have I achieved? Nothing. However, if somebody says, oh, I found out the value of the metric and its first derivative at that point, so I know something about the sphere, you can say, no, sorry, you don't know anything about the sphere from that. Okay? And the main use for us is it guides us to the fact that curvature will be judged by knowing not the metric, but the Riemann curvature tensor, which even knowing it at one point tells you something about that point. Okay? It is some tensor made out of second derivatives of the metric. Many linear combinations of these things. I mean, the linear combination of many of these things. There are 4 in this. It's very complicated. But once we find it, whatever it is, if it's 0, then we can really say the metric is trivial at that point, meaningfully so. Okay? Because then the curvature is 0. That's why we call it the curvature. So there are 3 basic objects in the game: the metric, the affine connection, and the Riemann curvature. We have encountered 2 of them. But here is the warning that these 2 don't encapsulate enough information if we just look at a single point. But from here onwards, there is some information.
So, can't we think that making the metric at a particular point to be identity and its first derivative to be 0, it looks like flat in that sense?
It looks like flat, but very little bit like flat, because only at a point.
Yeah, one.
Yeah. By the way, one more point I'll make. Perhaps I should have connected this up, but I think you know this now. You recall my equation: box h mu nu equals plus dot dot equals minus something t mu, right? So what is this quantity? This is a fluctuation of the metric. What does this do? Takes the second derivative. So this equation determines the second derivative. It doesn't determine the metric or the first derivative. Completely consistent with what we are saying, because this equation is like what information does the stress energy of a matter distribution give us? It gives us information about second derivative of the metric, and that's the thing we want to know. It doesn't give us information about the things that we didn't want to know. Yeah, question? Somebody was saying something. Okay, so if not, then thank you. We need another.